ಇದು ಅಟೆಂಡೆನ್ಸ್ ಇದು ಗೊತ್ತಾಗುತ್ತಲ್ಲ ಸರ್.
ಈ ಕಡೆ ಕುತ್ಕೊಂಡು 5 ನಿಮಿಷ ಇಂಟ್ರೊಡ್ಯೂಸ್ ಮಾಡೋದು.
ನವೀನ್ ಸರ್.
ಡಾಕ್ಟರ್ ನವೀನ್, ನಮಸ್ಕಾರ.
Namaste.
Ramesh from Karnataka Science and Technology Academy.
Thank you, sir.
Thanks for joining.
My pleasure, sir.
Doctor, start ಮಾಡೋಣ.
Sure, sir. Sure, sir.
Let me, I welcome all the participants and dignitaries to the webinar session on alternating current. We have with us eminent speaker, Shri NAVEEN Mascharanis, to deliver a talk on alternating current. Before starting the talk, let me briefly introduce the achievements of Mr. NAVEEN. Presently is serving as associate professor at the prestigious St. Aloysius College, and he has been serving there since June 1995. Mr. NAVEEN has served as NSS program officer at St. Aloysius College for 6 years, from 96 to 2002, and he has obtained his MSc from Mangaluru University in 1995, and at present he is pursuing his PhD and under Visvesvaraya Technological University. Mascharanis has served as secretary of St. Aloysius College Staff Association during the academic year 2006-7. He has also served as secretary, treasurer, joint secretary at St. Aloysius College Alumni Association, and he is the chairman of Board of Examiners in Electronics for Mangaluru University. He is also the coordinator of UGC scheme College with Potential for Excellence for the period 2010 to 15, with 2.8 crore worth project sanctioned by UGC. He has also been appointed as NAC coordinator the academic year 2015. He is also the IQAC coordinator of the college from 2018 to 2021. He is the head of the Department of Computer Science since 2013 to 2020. Now he is the chairman of Board of Studies and Board of Examiners of St. Aloysius College. And with this background, I once again welcome Mr. NAVEEN Mascharanis to this webinar. Request him to deliver his distinguished talk on alternating current. At this juncture, I take this opportunity to welcome our esteemed member of KSTA, Dr. Eknath sir. Sir, welcome to you, sir. Yes, there are many participants who have joined on Cisco WebEx and many more in YouTube platform. They will be listening to Mr. NAVEEN Mascharanis talk. Sir, with this background, over to you, Mr. NAVEEN, for your talk. Thank you.
Thank you, sir. So once again, thanks for this opportunity. The first kind of experience, to teach for the Karnataka state through online platform, to the +2 students. Thanks to all those who suggested my name and for making this happen. Great moment. So let me begin. I am here to discuss alternating current. Most of you know by now what is direct current, a quantity which remains constant with time or even varies with time. That is called DC, variable DC, or a steady DC, direct current. But this is alternating current. What is the definition of alternating current? We will see the definition. But before that, before I really kick the start of the topics, let me tell you the methodology that I would like to follow, and that is this one. First, let me give the introduction to the subject and the highlights of the topic. By learning this topic, what will happen, topic by topic discussion and mention of important points is the next idea. And in addition, information as and when it's required for better understanding of the subject, and then objective questions 1 or 2, and then the conclusion summary. So this is what I have planned for this 1 hour. And now, yes, as I told you, the introduction, what you will study in this chapter. In this chapter, you will study not just the characteristics of AC, but also the application of AC to the components that by now I think all must be knowing: resistor, capacitor, inductor, and the combination, series combinations and parallel combinations. What will happen when AC is applied to R, L, C, similarly the series combinations of these components and parallel combinations of these components. That's what we are going to see in this chapter. And also at the end, how we can transport AC from one point to the other, what are the advantages of AC and compared to DC and so on. So that is the highlight that we are going to get in this chapter. Define AC. If that is the question to be answered, then the quantity that varies continuously with the time and also reverses its direction periodically is known as AC. To put it in a simple way, in mathematics, we all must be knowing that there is a wave, called sine wave, right? So if I have to write, this is a sine wave, right? It may not be a perfect sine wave, but this is how we write a sine wave. Sine wave is the best example for this AC because sine wave is a periodic function. All the values of sine lie between +1 and -1, right? Okay, so that's what we know. So that's how we use this sine wave or a cosine wave to represent AC better. If this is 0, this is +1, and this is -1 in sine. And here, if you see, how I have defined now AC. AC is a quantity which varies continuously with time. If at all, if this x-axis is time now, you see, as time goes, the value goes on increasing here, positive half cycle. This is called positive half cycle, reaches its maximum, comes down again. And then, in this duration, that the quantity has reversed its direction. Again, for the same duration, it will be in this direction, positive half cycle again. For the same duration, it will be negative half cycle. So is it not periodic, a change of positive and negative half cycles? Yes. So the word periodically is very important. What's the meaning of periodically? At regular intervals of time. Okay, regular intervals of time. So that's the meaning of periodic. Now, mathematically, again, not just to represent AC. If somebody asks you to write AC, how you can write? And that's what is shown here. If the quantity is voltage, how we can write AC voltage? V is equal to V naught sine omega t. Now, each term will be explained to you a little later, but then you all know that this is a sine function now again. So sinusoidal, the one which I've drawn on the top here. So this is how we represent AC. So AC has a positive half cycle and a negative half cycle. So what is one complete cycle, therefore? One cycle of AC will have one positive half cycle, allow me to write this way, plus one negative half cycle. Okay. So if you ask me, maybe, what is the definition of cycle in AC? It is that portion of the waveform which keeps repeating again. For example, so I've already drawn the sine wave. So this is one cycle because afterwards, if I were to draw again, the same thing I'm going to draw again, correct? So this is one cycle, right? But if somebody says, no, I will start the measurement from here along the exact direction, then it should stop here. The same point should start. All right, this is one cycle. So cycle can be defined that way. That portion of the waveform which keeps repeating is referred as a cycle. Okay, so let me move forward. So these are the important terms of AC that we all need to know. That is time period. What is time period? the time taken to complete one cycle. For example, if I write once again the sinusoidal waveform, which is this, okay, the time taken to complete one cycle. So which is one cycle now here? As I told you, if I start the measurement here, it will stop here, correct? So this is your time period T. Time taken to complete one cycle. So if I make a, when we were small, we were all doing this now, number of cycles. Okay, if this is one column and if this is time. So for one cycle, the time period is called T. So once again, let me tell you what is time period. Time period is nothing but the time taken to complete one cycle. What is frequency? That is the next term. This is done. What is frequency now? This one. Number of cycles passing through a given reference point in 1 second. So here, the time period is not T now. In 1 second, how many cycles? So that is called frequency. Frequency is, is the English word. For example, we ask this question always: how frequently the buses arrive at your bus stop, at our bus stop? You may say, no, many times, half an hour, one bus, 5 minutes, one bus. Correct? That's a frequency of bus. If you say half an hour, one bus, the frequency is less. If I say one bus in a minute, every minute there is a bus, then the frequency is more. Correct? So if you now see here very carefully, this calculation of mine, you need to cross multiply, right? In 1 second, how many cycles appear? That is frequency. So how many cycles will appear? So that is 1 by T. And that is called frequency. Okay. Everybody knows that F is equal to 1 by T, but many times I ask this simple question to the students: how do you get this F is equal to 1 by T? They fail to answer. They do not know that these two are interconnected. I mean, these are interconnected, they know, but how this comes, God only knows. It's simple, no? What is time period? Time taken to complete one cycle. So for one cycle here, time period is T. In 1 second, how many such cycles come? So cross multiply, you'll get 1 by T. So in India, Indian mains, I think all of us know that the frequency of our AC mains is 50 Hertz. So what's the time period therefore? That is time taken to complete one cycle. It should be 1 by 50, right? And 1 by 50 would be 0.02 seconds. So which means this from here to here, 0.02 seconds. So you can imagine, in 1 second, this is just 0.02 second. In 1 second, 50 such cycles will come, and that is frequency. So in 1 second, 50 cycles appear. That's the frequency of Indian main. So I think by now, therefore, you must have understood the relation between, not only the relation between period and frequency, but also the definitions of period and frequency. Next definition, so is instantaneous value. As the name itself suggests us, instant means at any point of time. What is the value? At any point of time, what is the value? That is called instantaneous value. If I have to take you back to the formula here, which I wrote mathematically, how to write AC, V is equal to, for voltage, V is equal to V naught sine omega t. Here is said the left hand side, this one, this is insta value. I mean, to be short, it's not Instagram value, it's an insta value, it's an instantaneous value. All right, good. So that's the instantaneous value of AC, right? What is amplitude now? Amplitude also is referred as, you can make a note of this, it's also known as peak value, right? The maximum value attained by an AC quantity in any half cycle. So you know that AC cycle has two half cycles, positive half and negative half. So this is known as either this or this. So the y-axis can be either voltage or current. These are the instantaneous values, because at this instant, this is the value. Now, let's say if this is 10 volt, half of that would be 5 volt, right? So at next moment, it will be like this, and so on. It keeps on changing. But what is peak value now, or amplitude? Amplitude or peak value is the maximum value taken by an AC quantity in any of the half cycles of AC. either positive half cycle or negative half cycle. Are they same? If this is 5 volt, if the total peak value here is 5 volt, this also is 5 volt. So here, therefore, I would like to introduce to you what is known as also peak to peak value. So if at all, if somewhere they give you in a problem peak to peak value, don't think that it was a mistake of print, okay, that they should have given you only peak value and not peak to peak value. Peak to peak value means it's a value from negative peak to the positive peak. So it must include this 5 as well as this 5. So how much will be the peak to peak value? 5 plus 5, 10 volt. So what would be the relation between peak to peak value and peak value? Therefore, peak value will be half of peak to peak value. I repeat, peak value will be always half of peak to peak value. Okay, so that is I naught or V naught. Why I have given 2 here? One is for the current and other one is for the voltage. So I told you, here in this waveform, the y-axis can be either V or I. Okay, right? Good. So let me remain in that slide because I'm not finished. Next one, the mean value. The mean value, or also it's called average value, denoted by VM or IM, is the, sum of the instantaneous values taken over only half a cycle. Okay, it is summation of all the instantaneous values taken only over half a cycle. Why it is not taken over a full cycle, I'll tell you. This is AC. This is positive half cycle and this is negative half cycle. For every positive value, let's say for +1, is there a -1 in AC? Yes. So if you add +1 to -1, what will be the value? 0, right? So if you take the average of the instantaneous values of AC over the entire cycle, its value will be 0. Okay. So what's the average value of AC over a complete cycle of AC? It's 0. That's the answer. But is it defined over a full cycle? No. Mean value is defined for half a cycle. Okay. So let me try to erase a little more here so that we can write a little. Yeah. Okay. Trying to erase. Let's see. I think it's not possible. Fine. I hope we can manage. Let's see. The average value is defined not for full cycle, but only for half a cycle. Why it cannot be defined for a full cycle? Or you may ask at this point of time, is there something in AC which is defined for full cycle? The answer is yes. That's the next one. Next one. Peak value is not defined for a cycle also. It is defined at a point, no? Because peak value is only at this point you get the highest number. So mean value is defined for half a cycle. I'm trying to, highlight that. But it is only the RMS value which is defined for full cycle. So let me go to the next slide to write about RMS and mean value because there is place here. So if at all, if you want to know how much is the average value of AC, it will be, 2 V0 by I, or it's just, let me correct it. It's going to be 0.637 times V naught. It's going to be V0 by pi. Okay, fine. 1 by 3.14 times the average value. Okay, as I told you, it's the average of the insta value taken over 1/2 cycle. So it will be this 1 by pi, that is the average for half a cycle. Okay, because if this is 0 here, this is pi, this is 2 pi. You all know this. So 1/2 cycle is, it's only, if you take 0 to pi, it is pi. Even for prime 2 pi also, it is pi only. So 1 by pi integration of 0 to pi. That's when you take integration, when you want summation. And that's what I said. It's the average of summation of insta values. So what is the full form of this V? It's going to be V0 sine omega t. If you take this integration, and substitute the limits, okay, you will find that the answer will be this. The answer that you get will be this. Okay, so that's what we are trying to say. So, okay, fine, good. So next comes the RMS value. What is the full form of RMS? Root mean square. So as I say, I will try to write, it's root of mean. Mean means average again. But this time it is taken over full cycle. Therefore 1 by 2 pi. Square of instantaneous values taken over complete cycle. So if at all, if I told you additional information, if they ask you which among the following is a RMS quantity, and if they give you this as option A and then B, C, D, and all, so this will be your option. Okay, root of average of square of instantaneous values taken over one complete cycle. Okay, that will be VRMS. And what will be the answer of this? After you take integration and substitute the limits, V0 by root 2. And what is 1 by root 2? It will be 0.707 times V0. 0.707 times V0. Okay, so this was 0.637 times V0. 636. This is 0.707 times V0. So now the tricky question is, if I ask you out of, I'm writing here at the top, right left corner, if I ask you among V0, Vm, and VRMS, compare these three quantities or give the relation between these three quantities, the relation would be VO is always the greatest, smaller than Vm, VRMS, and the smallest one is Vm. This is the only relation which is correct. Because VRMS is, this, VRMS is 70.7% of V0, whereas Vm is 63.7% of V0. Correct? So that is what we need to know about our the RMS value, and which is the quantity which is defined only over a full cycle. That also we know now. Correct? Which is that the only quantity which is defined for the entire cycle is RMS. What is the full form of RMS? Root mean square. And did I write the mathematical equation for this? Yes. Root of 1 by 2 pi times integration 0 to 2 pi V square d omega t. What is the substitution for V here? This is the instantaneous value. We know that V is equal to V0 sine omega t. Correct? Two. It should have been 2V0 by pi. I made a mistake, I think. So let me correct it. 2V0 by pi. And that will be 0.637. Okay, fine. So let me go back and see whether all the points are defined. Yes. We said what is period of t? Period t, time taken to complete one cycle. What is frequency? Number of cycles per second. Instantaneous value, value at any instant. Amplitude, the maximum value taken by the AC quantity. Average value, which is defined only half a cycle, it's going to be 0.637 times V0 or 2V0 by pi. RMS value, it's going to be V0 by root 2. And how much is 1 by root 2? Root is 1.414. So 1 by root 2 is 0.707. The last one which is remaining is the phase of AC. And that is my next slide. Phase. This was a slide. Phase. So how to define phase? Phase has a very interesting definition. The time lapsed or the distance covered once the AC quantity has passed 0, that is this is 0, in the positive direction, that is this. See, when somebody runs in a track, okay, if there is a commentator who is explaining how the person is running, you can always explain in two ways, no? Is the phase with which the person is running. He ran this distance, let's say 500 meters in 1 second. Or you can say in one, 1 minute he was running, he ran, let's say 200 meters, something like that. So you can always explain the phase either in terms of time or in terms of the distance. But when it comes to AC quantity, it won't be the linear distance, but the angular distance, correct? Angular distance. Therefore, it is measured in, degrees or radians. Angular distance covered or the time lapsed once the AC quantity has passed to 0 in the positive direction. Okay? Right? Once the AC quantity has passed to 0 in the positive direction. So if I ask you, this is, okay, this top diagram is of V. If I write here, what is the phase of V at point B? And where is point B? Let me write where is point B. This is point B. What is the phase of this quantity V? That is the top diagram, this waveform. Let me write over it, this diagram. What is the phase of this V at point B? You can say that the phase of V at point B is either T by 4 seconds, or you know that in terms of degrees, this is, radians, this is 0 radians, this is pi by 2 or pi by 2 radians. Either T by 4 seconds or pi by 2 radians, correct? So that's what is, the phase of V at B. Similarly, what is the phase if I mark here, what is the phase at C? You can say phase of V at C is T by 2, because this much is T, no? From here to here it is T. So what is half of that? It will be T by 2. So either T by 2 seconds, because after passing 0 in the positive direction, it has taken this time, T by 2, to reach there, here, to C, this point C. Or in terms of angular distance, which is measured in radians now, it is pi radians, or pi. So I think by now you almost have understood how to define phase. Phase is the amount of time lapsed or the angular distance covered once the AC quantity has passed reference point, and the reference point we shall take it as 0 in the positive direction. Once the AC quantity has passed to 0 in the positive direction. Okay. So now we need to apply this AC to the components that we know. And the components that we all know are 3 of them. Resistor, which is the only component which dissipates energy in the form of heat. And then capacitor, which doesn't dissipate energy but stores energy, electrostatic energy. Okay, half Q square by C, you all know this. And then we have a coil bound over a core, which is known as inductor, okay, which also stores energy in its magnetic field, magnetic energy. Okay, so what happens when AC is applied to these components? Only pure resistor. So when I say resistor here, understand it's a pure resistor, pure capacitor, pure coil. Okay, pure resistor, only resistor. What happens? So, which means I'm going to apply AC across resistor, which is V is equal to V naught sin omega t. I need to calculate how much is the current flowing through this resistor, and whether this current and voltage are in phase or out of phase. Remember, when two people run a race, we can always say, no, the two people were running in phase. If the two people are running at all times in phase, then both should be the winners. But if there is a slight difference between the two people who are running, then we say somebody is leading, somebody is lagging. No? So whenever there is out of phase relation, then always there is a lead and lag concept. Okay. If A leads B, we know that B lags A by the same amount. For example, when two people are running the race, if I say A is ahead of B by 50 meters, other way of saying is B is behind A by what? It's not 100 meters, no, it's by the same amount, that is 50 meters. So what is the inference when AC is applied to a resistor? When AC is applied to a resistor, if AC is defined this way, V is equal to V naught sin omega t, don't think that AC should be written always as V is equal to V naught sin omega t. I can write it as V is equal to V naught sin omega t plus pi by 4 also. Or you can say that it is sine of omega t plus pi by 2 also. Okay, so that is cos omega t actually, whatever. So if at all, if this is the AC that is applied, then what will be the expression for current through the resistor? Since we know that when AC is applied to a resistor, the current through the resistor and the voltage across the resistor, IR and VR, are in phase. That means, if at all, if I denote phi as the phase difference between the two, then this phi difference, the phase difference will be 0 degree. Is there a phase difference between current through the resistor and voltage across the resistor? In this diagram, current flowing through the resistor I and the voltage applied across. At all times, the current flowing through the resistor and the voltage applied across the resistor are in phase. So, which means, what is the phase difference? The phase difference is 0 degree. So, for V is equal to V naught sin omega t plus pi by 4, if this is the voltage that is applied, if they say to you, then ask you to write the expression for current, then you must confidently write I naught sine of omega t plus pi by 4. Okay. What about the average power in a resistor? Does the resistor dissipate energy? I said yes, in the form of heat. You can always say that general formula, P at any instant you can calculate, no? As equal to V into I, where V is equal to V naught sin omega t, I is equal to I naught sin omega t. So which means V is equal to, V naught sin omega t, and I is equal to I naught sin omega t, means it is V naught I naught sin square omega t. That's how sin square will come here in this picture, equation. You know how you should not get surprised from where this sin square omega t came in. So average power is equal to I naught square R into sin square omega t. So we know that there are three forms of power. No, one is V into I, other one is I square into R. This for DC I'm writing V square by R. Similarly here in AC also. So we are writing V into I, but you can write it V into, at any instant. What we write? I said V into I at any instant. Correct? No, at any instant. So otherwise it is V naught sin omega t into I naught sin omega t. But can't I write I naught in terms of V naught? Yes, it will be V naught by R. Then this becomes V naught square by R. Or instead of doing this, can I write V naught in terms of I naught? Yes, V naught is equal to I naught into R. And this is I naught itself. Then it becomes I naught square into R. So when I take average, you can't take the average of this, but we can take the average of this function sin square omega t. And all of you know the average of sin square omega t is half. The average value of sin square omega, this is the notation for average, okay? Angular brackets. The average of sin square omega t taken over the entire cycle will be half. And that's how the formula comes as half I naught square into, sorry, it will be not half, it will be 1 by root 2. IRMS is I naught by root 2, right? Root 2 the whole square, that is I naught square by 2, correct, into R. So it's half, right? So that's how this comes as half I naught square by R, or it is in terms of IRMS. What is the relation between IRMS and I naught? IRMS is equal to I naught by root 2. I naught by root 2 the whole square, okay, into R, right? So that's how this half should have been here, I believe. Okay, so we'll see in the next slide what is the mistake. Okay, before we go there, so this is how we get that P average is equal to, I naught square R sin square omega t. And you can take the average of sin square function over the entire cycle, okay, and you will get that value, and then divide, you will get the average value. But is it 0? No. The average value of power in the resistor is never 0. So next we have to define what is called phasor before we proceed further. Phasor is a rotating vector. It should have started with this, okay, origin. Sorry for that error. Okay, now these are the two arrow marks. This is actually I naught. This is actually V naught. For example, if these are the two quantities, one is V, other one is I, like this. Are they in phase? Yes. It may not look like in the picture, but they are in phase. This is V and this is I. Okay, they are in phase. This is how I draw the phasor diagram. What is I naught? I naught is this. And how much is V naught? V naught is this. So V naught is bigger than I naught. That's what I've shown here. Okay. Okay. And this is the angle, phase angle. Are they having the same phase? I naught and V naught at this instant? Yes. Can I draw this picture this way also? This is what happens when AC is applied to a resistor. Okay. This is a picture of AC applied to pure R. Can I draw it this way also? This is I naught and this is V naught. Answer is yes. Or in this quadrant also? Yes. What is the difference? The difference is they are drawn at different instants. Please understand this is from 0 to 90 degree. That means you are here. Shading. I will do this one. This is 90 to 180 degree. That means you will be here. So a cycle has got 2 half cycles, but believe me, a half cycle also has got 2 quarters, no? So quarter half cycle. This is from 180 to 270, and the last is 270 back to 360. So different instants there. What is phasor therefore? It's a rotating vector. Okay, rotating vector. And let me tell you, I can take the vertical component here and the vertical component here. What the vertical components represent actually? The instantaneous values. Vertical component actually represents the instantaneous values. So in case if I now write this as I naught and this as, oh, okay, sorry for that diagram. Let me rewrite that. Okay, here let us, it should be straighter. I naught and this as V naught. Okay, this is 90 degree, remember. This itself, what is the vertical component of this? This itself is the vertical component. What's the vertical component of this one? This itself. So I naught is I naught itself, correct, no? Which means you are at which angle? 90 degree. But if somebody says, I will draw this way, I naught and V naught. But if I ask you what is the instantaneous values of I naught and, I mean this I and V, it's 0, right? And this is angle 0, correct. At 0, you only start, no, here, we are here. Vertical component always gives you the instantaneous values. I hope you understood that. This vertical component always gives you the instantaneous values. Okay, so that's about phasor. So let's move forward to the next. That is AC applied to an inductor. That means AC applied to a coil. Let me draw that picture for you. That is this. We all know that there will be voltage induced whenever flux linked with the coil changes, and the voltage induced will be always VL is equal to, magnitude. If you take it is L into DI by dt. We all know this. Okay. For the same voltage, if at all, if you are writing V is equal to V naught sin omega t applied, what will be current? Current through the coil always lags. Please remember, therefore, in AC, let me write it here. In AC, if coil dominates, or if only coil is there, here only coil is there. How do you know that only coil is there? Somebody may say, along with the coil, R is also there. No, yes, true. But you have to imagine here that this is the ideal coil. What is an ideal coil? A coil which has 0 resistance. Can we think of that? A coil which has 0 resistance? No. All coils have resistance. Maybe negligible, but it has. So very difficult to, show do this practically and show in the lab. But then we can always imagine, a pure inductor. Remember that was a pure resistor. This is a pure inductor. What's a pure inductor? An inductor, a coil whose resistance is 0. So if coil dominates, then current always lags. Current through the coil lags. But since this is a pure coil, the lag is exactly by an angle 90 degree. So V leads I by 90 degree is same as saying I lags V by 90 degree. An inductive reactance. Is there opposition? What is reactance? Is it similar to resistance? Yeah, that is for DC circuit. This is for AC now. Opposition, resistor behaves the same way in both AC as well as DC. But now the coil and the capacitor, they behave differently in DC environment and AC environment. The opposition offered by the coil to the flow of alternating current is called inductive reactance. Reactance is denoted by X. And to make it inductive reactance, it is XL. And XL will be equal to omega L, and omega L, we all know what is omega, it's angular frequency. So it is 2 pi FL. unit of this is same as that of resistance, and that is ohms. So that is inductive reactance. If at all, if you want to plot, with frequency, the variation of XL, please remember XL depends on only two things, not on 2 pi. 2 pi is a constant, no? It depends on F and it depends on L. So if I want to plot, this is like y is equal to mx graph, therefore, okay. So along the x-axis, let me try to plot, y is XL and this is frequency. Y is equal to mx, x is F and y is XL. What is the slope going to be of this straight line? Therefore, it will be a straight line. This whose slope will be equal to 2 pi L, no? So if they ask you a tricky question, what's the slope of XL versus F graph? You must be knowing that it is equal to y is equal to mx. So therefore, it is 2 pi L. 2 pi L is the slope of this graph. Slope is which is always y by x. It's going to be this. Okay. So let's proceed further to the next slide. So therefore, whenever you have AC applied to a coil, or if you know that coil dominates, what you are going to say? Current lags. That much should be clear today, at least by an angle phi, and that phi becomes exactly 90 degrees if it's a pure coil. For pure coil. Otherwise, will it be 90? No, it will be less than 90, but greater than 0. Anywhere between 0 and 90, depending on the resistance value of the coil. Power. As we discussed, power, power, does the coil dissipate power? That to pure coil dissipate power? The answer is no. It only stores energy, but it doesn't dissipate energy. Therefore, answer should be 0, and you got the answer 0 here. And therefore, they say current flowing through a pure inductor is called wattless current. Wattless current, because average power dissipated, for the entire cycle will be 0. Okay, that's why it's called wattless current. How did he calculate that? Again, P is equal to VI. We know that it is V0 sin omega t, but current lags. Please remember, in a coil, no, if voltage is sine graph, the current is minus cosine graph, and that is this. This is negative of cosine, and that's what is clear here, minus cosine graph. Because current lags voltage, so minus I0 cos omega t, and therefore we have sin omega t cos omega t, okay, and that can be written as sin 2 omega t, because you all know sin 2 theta is 2 sin theta cos theta. Okay, mathematics should be little good. What's the average value of sin 2 omega t? If you are calculating average value, it's average value over this. And all of us know the average value of sin 2 omega t is 0 over the entire cycle. This is going to be 0. And that's why the entire thing becomes 0. Not because V0 is 0. V0 is never 0. I0 is never 0. But this average value is 0. And that's why this will be 0. Whereas previously, it was the average value of sin square omega t, which is not 0. But sin 2 omega t, the average value of the entire cycle is 0. Okay, you can always see that. Fine. Next, AC applied to capacitor. This is just the opposite of AC applied to coil. Again, this is pure capacitor. The meaning is, what is a pure capacitor? You may wonder. Its metal plates again have, no resistance as such, and the perfect insulator in between the two plates. So pure capacitor, very difficult to imagine, but you can think of. If V is equal to V0 sin omega t is applied, please remember whenever in AC, if capacitor C dominates, then current always leads. Okay, leads by an angle phi, which can be anywhere between pi by 2 and 0. And when it will be exactly pi by 2, it will be only for pure capacitor. So therefore, we wrote plus pi by 2. Let me take you back to coil and just show you it was minus pi by 2. Why? Because current was lagging the voltage. Okay? Here, it will be current leading, and therefore, it's plus pi by 2. I leads V by pi by 2. Now, what is the opposition offered by the capacitor to the flow of AC? That's called capacitor reactance XC. which will be equal to 1 by omega c, not omega c, 1 by omega c. What is omega? It's angular frequency 2 pi f, and therefore 2 pi f c. Unit again is ohm. Okay. So once again, if you are trying to plot with the frequency, xc, then it will be this graph. It will be a hyperbola like this. Okay. Because as frequency increases, xc goes on decreasing. And it's only when f becomes infinity, xc becomes 0. Therefore, this will never touch the x-axis. Similarly, it will never touch even the y-axis as well. So when the frequency is 0, xc will be infinity. So it starts from infinity. So this part here and here will be parallel to the x-axis and y-axis. So this is the graph that you get for xc and f. Let's see in the next slide what we have. Again, instantaneous power. This also current flowing through a pure capacitor also will be called as wattless current. Therefore, wattless current is not just the current flowing through a pure inductor, but also current flowing through a pure capacitor as well. Because there also you found average power is 0. This time only minus I naught is not there because current leads. Now, if this is voltage graph, the current graph will be a positive cosine graph. Okay, this is positive cosine graph. This is current graph. So plus I naught cos omega t cosine graph. No, and therefore you have V naught I naught sine 2 omega t again, and the average value of sine 2 omega t is again 0. The reason why average value becomes 0. Average is denoted by these angular brackets. Okay, fine. Good. Next, now having found out AC applied to individual components, that is R, L, and C, now we need to think of the series combination of L, C, and R. What happens when AC is applied to L, C, and R? We all know that when AC is applied to L, C, and R, the voltages, that is the applied voltage V, voltage across R, voltage across L, and voltage across C do not add up numerically. V will not be equal to VR plus VL plus VC. No. It's a vector addition. So it will be V square is equal to VR square plus VL minus VC the whole square. This is because we all know current through R and the applied voltage across R, sorry. Current through R and current is the same, no, in series combination. But still, if I say that this is current IR and the voltage across R, are they in phase? Yes. But current through coil lacks. Current through coil lacks the applied voltage. So therefore, this should be VL then. Current is lagging. The same current. Current IR is same as IL is same as IC. But current through the capacitor is leading the current through the capacitor. This is the current through the capacitor. Current through the capacitor. Why it's like this? Let me just go to the pen again. Highlighter. No. Pen. Okay. Current through the capacitor is leading the voltage across C by an angle again 90 degree. So let's assume that VL is greater than VC. We can assume VC also to be greater than VL. Then if VL greater than VC, then can we get to this as a VL minus VC? Yes. Two vectors, no, acting in opposite direction. Can we have the resultant of that? Yes. Then we can have a rectangle here, and this diagonal is the applied voltage V. So this V, therefore, must be, by the current theorem, V must be equal to, that is square on the largest side, that the hypotenuse must be equal to VR square. And how much is this? This is VL minus VC. Or it can be VL difference VC, if at all if VC is greater than VL. So from there we get the definition of impedance later. What is impedance? Total opposition to the flow of AC by R, L, and C. Total opposition to the flow of AC by R, L, and C. That is impedance. Okay. So tan phi, that is phase difference, will be XL difference XC divided by R. Of course, it is XL minus XC by R. If XL is greater than XC, that is VL is greater than XC, or else it will be XC minus XL by R. So therefore, in general, it is XL difference XC by R. Okay. So how do you get that? That is this. See, tan of phi. You all know what is tan of phi, no? It is opposite by adjacent. Is it not VL minus VC divided by VR? And II gets cancelled, and finally we get only XL minus XC by R. As simple as that. From the same diagram, we will get all that. Okay. So let me go to the next. Resonance. So resonance we can discuss only when you have L and C. Of course, along with L, every L, R is free, no? Therefore, it becomes LCR. Suppose if in a problem, if they say AC is applied to LC circuit, you should not say that we don't know what is LC circuit. LC circuit is same as LCR circuit because every L has R. Because we are in a practical world where L has resistance, right? Okay. So it's series LCR circuit only can undergo resonance. And when that happens, when XL value and XC value, that is both capacitor and coil offer equal opposition to the flow of AC. And since they are acting in opposite direction, see, I told you VL is along positive Y direction and VC along negative Y direction. If VL becomes equal to VC, or that means XL becomes equal to XC, then what is a resultant of VL and VC? 0. Right? In this big diagram, if you want to see, VL, if this becomes exactly equal to VC, then the resultant is 0. So your V slips over this line. V becomes equal to VR. Applied voltage will be entirely across the resistor. At resonance, therefore, I have written XL becomes equal to XC. Since the entire voltage is across the resistor, the circuit is purely acting like resistive. Total opposition is only of the resistance because other two are getting cancelled out. And the power factor, which is always cos of phi, okay, and phi is 0, and you all know what is cos 0. Cos 0 will be unity. These are the characteristics of resonance. Circuit is said to be at electrical resonance when the current through the circuit is maximum. And current will be maximum because I is equal to always V by Z. And Z is equal to R now. Otherwise, what is Z? You know from the previous diagram, what is Z? Z will be this. This is Z. But I have blocked no is Z. And that's how you got Z is equal to V by I. Root of R square plus. That means something will be added to R, no? So that's why when something is added to R, Z becomes heavier and current becomes smaller and smaller. So the maximum current you get only when Z is equal to R. Z is minimum. And the minimum value of Z is always R. And if at all Z is minimum, then the current should be maximum because Z is in the denominator. And at which frequency this all happens? At a frequency where XL becomes equal to XC. That means at a frequency F0, where 2 pi F0 L becomes equal to 1 by 2 pi F0 C. And if you cross multiply and check, F0 will be equal to 1 by 2 pi root LC. The unit of this will be Hertz. If I ask you what is the unit of root LC unit is time, no? Seconds. Because frequency is always 1 upon time. 2 pi cannot have a unit, it's a constant. Therefore, root LC has a unit of time. Okay. Sharpness and bandwidth is what we are discussing now. Sharpness and bandwidth. Sharpness is always described in terms of factor called quality factor in physics. And the resonance curve I'm drawing for the first time here, it will be something like this. And this is my resonant frequency F0, where the current has become maximum, which is V by R. Other places it is all V by Z. So can I have, now, if this is Imax, can I have a position called Imax by root 2? The answer is yes. You will find 2 points here on the curve. Those are called half power points because compared to the point here, maximum point, the power consumed will be half. Because power is always in a resistor, distributed by resistor. It is I square into R. It's always I square into R, isn't it? I naught square into R, I max square into R. But at this point, current itself is I max by root 2. What is I max by root 2? The whole square. I max by root 2 the whole square is I max square by, that is I naught square by 2. Therefore, root 2 the whole square is 2. Your power becomes half. And that's why these points are called half power points, because at these points, you can mark them as A and B if you want. They're called half power points because power consumed by the resistor at this point will be half compared to that at maximum. And if the corresponding frequencies here, if I write F1 and if I may write this as F2, they are called half power frequencies. These are frequencies at which the current in the circuit is 1 by root times the maximum current, or the power dissipated is half the maximum value. And the difference between this F2 and F1, that is this, is denoted as bandwidth, whose unit is hertz. And the sharpness, which is described by the quality factor, is always defined as the resonant frequency upon bandwidth. And from that you can understand resonant frequency is 1 by 2 pi root LC, and bandwidth can be always shown as 2 pi R by 2 pi L. Here it is. We can take down this extra formula. Bandwidth can be also shown as equal to R by 2 pi L. So if you put this R by 2 pi L here, okay, L goes up, okay, 2 pi also goes up. It all get cancelled, but R comes down. You will get this formula, 1 by R root of L by C. Of course, we can also find out the same quality factor. Quality factor is defined only at resonance, okay? Q factor is defined at resonance. And you can find out the quality factor using two more formulas. That is, Q is equal to XL by R, or Q is equal to XC by R. But XL value and XC value are equal at resonance. You all know it. And how much is it? It is also equal to root of L by C. Additional formula again. As I told you, I'll give you additional points. So these are all additional points. XL is equal to XC is always equal to root of L by C. So that time I said root LC unit is time. What is root of L by C unit therefore now? Root of L by C unit will be ohm. Because XC is ohm. XL is ohm. Therefore root of L by C also must be ohm. So the formula to calculate the quality factor will be, yes, will be either XL by R, or it will be XC by R, or it will be 1 by R root of L by C. So this is ohm, this is also ohm, so ohm by ohm. So Q is dimensionless. That's what we know. Q is always dimensionless quantity. Okay, so that is sharpness. If at all, if I draw in one more color, let's see if I can get that here. Different color. Yes, here is a different color. If I draw one more waveform here, and if I ask you which one is sharper, if this is first waveform and second waveform, you will say second waveform is sharper because it looks sharp, but it has got more current. Now maximum is more. It's always V by R. No, R is small, so R determines the sharpness always. Of course, L and C also determines, but it is a ratio of L and C that determines. But if R is less and less, okay, current will become more and more. The quality factor will become high and high. Higher the quality factor means more sharp is the resonance curve. Okay, so R value has so many times they ask us always, so in LC, what is the role of R? Because in resonant frequency only L and C is involved, no root 2 pi root LC. What's the role of R? R determines always the sharpness. Okay, R determines the sharpness, and therefore it also determines the bandwidth. Because if R is smaller and smaller, sharpness is more and more, but the bandwidth is smaller and smaller. Okay, bandwidth is the range of frequencies above which the current or the voltage is almost the maximum. Okay, power in AC. This is a general formula for power. The average power is always the product of what we call this as apparent power and what we call this as power factor. So when we buy an inverter, we always buy inverter of 400 VA because you do not know what we are going to connect to this, inverter. We may connect inductive components, we may connect capacitive components. Therefore, always the inverters are sold with apparent power. Okay, and it will be always multiplied by the power factor to get the actual power. So actual power is, so 400 VA doesn't mean that we can operate that inverter on 400 watt, worth appliances. No, it will be lesser than that because power factor for commercial usage will be, let's say, around 0.8. It cannot be more than 1. The maximum is 1. Let's say it's 0.8. Then this will be 320. And that is the actual power. You can use, let's say, 75 watt fans. You can calculate maybe 4 fans you can use on this, not the 5th one. So many times we may say only even the 5th one should work. No, it won't work, let's say. Which becomes more than 320. We multiply this 75 by 5. Only 4 fans will work. The 5th one, it will trip off. Because the manufacturer always sells the items based on not the actual power, but the apparent power. And that will be multiplied by the power factor, which is decided by the resistive, capacitive, and inductive component. Phi value will be anywhere between pi by 2 to 0. So cos phi also can be calculated now from this graph of your phi V. This is VL minus VC, and this is VR. This was the voltage triangle that we had. If you take cos phi is always adjacent by hypotenuse. So it is VR by V. It's going to be VR by V, and VR is I into R, V is I into Z. I will cancel, and therefore it's R by Z. I've already mentioned about this. Current flowing through a pure capacitor or coil is known as wattless current. LC, this is called tank. This is parallel combination of L and C, remember. And can we generate AC using this tank? Yes, but it gives you damped oscillations only. Why? Because this tank has a leakage in the form of invisible radiation, and in the form of, because the electrons flow through the wires, which have resistance, and therefore there is power dissipation in the form of heat. Therefore, the 2 types of losses are there. One is called heat, other one is radiation. Okay, because of which we don't get undamped oscillation, okay, in LC oscillator, but we get what we know as damped oscillations. But at any point of time, energy stored in a tank must be equal to energy stored in these 2 capacitors, these 2 components, capacitor and inductor. This is LC circuit, but not series combination, but parallel combination of L and C. If at all, if you can think of, supplying energy to this tank to the tune of how much it has lost. Let's say if it is losing some amount of energy, you can imagine a water tank. Let's say it's a leaky tank. Once water is constantly going out, but as the water goes out to the tank, if you can pour same amount of water, do you think that in the tank you will have the same level of water at all times? Yes. So that's how we can understand. So then, who can supply energy? You may ask me. Transistor circuit can supply, and then it becomes a real circuit in which you can get oscillations, sinusoidal oscillations, undamped. Okay. The maximum energy stored in a capacitor, all of you know, it is half Q naught square by C, where Q naught is equal to C into V naught. And the maximum energy stored in a coil will be always half L into I naught square. Okay, half Li square. Good. At this point, I also want to tell you something which I learned. If at all, if you know the energy stored in a capacitor, you see as half CV square, correct? Then you replace C by L and V by I, and vice versa. You always get the equation for the coil chapter as well. So it's very easy from magnetism to move to electrostatics to magnetism and vice versa. You have to just replace C by L and vice versa, V by I and vice versa. One more example, if you want. Now we all know for a capacitor C is equal to for parallel plate capacitor epsilon naught A by D. Similarly for L also, C replaced by L, epsilon naught, this permittivity, you should replace by permeability. A will be there, L will be there, but of course N square will be added. This is for a cylindrical coil, we write L depends on these components. All these we know, correct? So this is how easily we can move from chapter capacitor to coil. So transformer, as the name says, transforms AC. So AC can be easily stepped up or stepped down using step up or step down transformer. For an ideal transformer where there are no losses, NS by NP must be equal to VS by VP. This NS by NP is known as turns ratio. Therefore, this is all is equal to T, turns ratio, but it is equal to not IS by IP, but IP by IS. Okay. So this is for ideal transformer, but for practical transformer, Vs by Vp is never equal to IP by IS, but it is eta times IP by IS, where eta is known as the efficiency, and the efficiency is defined here. Is the ratio of output power to input power, that is Vs into IS divided by Vp into IP. So that you get here only. See here, what is eta from here? Cross multiply. Is it not Vs into IS divided by Vp into IP? Yes. Therefore, this is the general formula. Vs by Vp is equal to eta times IP by IS. Eta is equal to 1 for an ideal transformer, and therefore Vs by Vp becomes equal to Ns by Np. It is also equal in terms of the impedance, if you want, it is root of Zs by Zp. Okay, right? So these are the relations you should know. And eta value will be always less than 1 for practical transformer, because in a practical transformer there are losses. And which are the losses that we have? There are 4 losses. Losses which are, transformer means you know that there are 2 coils wound over a core, no? One is called primary. Anything which is connected to the source of energy is primary. Connected to the circuit is called secondary. And we know these are the 4 losses: heat loss, leakage loss, eddy current loss, hysteresis loss. How to minimize the heat loss? You need to select a very good wire of thickness, proper thickness. Okay? So proper thickness of the wire, you can minimize. You can make it 0. Proper thickness will allow you to make this heat loss less. Flux leakage, by winding on a proper core, you can wind one over the other, what is called tight coupling. Okay, so the winding will decide the loss. How the eddy current loss, it is a loss happening in a core, so you can think of a laminated core to minimize this loss. Instead of going for a big chunk of solid iron, you can laminate it, and this is how the picture always will be shown of a transformer core. These lines always say that it is all sliced, okay, and pressed with the help of insulating material. Hysteresis loss, once again, a lot of energy is spent in magnetizing and demagnetizing the core. Now, during positive half cycle, it is magnetized with one polarity. During negative half cycle, it is magnetized with the negative other polarity. So this energy spent in the core in the form of heat cannot be recovered. So that is again a loss. So we can do this by selecting a proper core, proper material of the core. That's why we say soft iron core and all that. Okay. So these are the 4 kind of losses that happen in the transformer. If we can minimize this or make it 0, then it is ideal transformer. Otherwise, the eta value for remaining transformers will be less than 1. Closer to 1 is best. Okay. That's all we have. I think I'm open for questions. I will wind up by just saying, what we studied. We studied what happens when AC is applied to R, L, C, and RLC. But from this, we can also find out what happens when AC is applied to RL and RC as well. To quickly say what happens, the Z value, that the general formula was root of R square plus XL minus XC the whole square. What happens to RL circuit? It will be root of R square plus XC is not there because capacitor is not there here, only XL square. Here what happens? Root of R square plus only XC square. If at all, if you go by the formula phi, then this will be general formula is tan phi is equal to XL minus XC by R. And formula will be tan phi is equal to XL by R here, tan phi is equal to XC by R here. Similarly, you can find out what happens to the impedance, the phase difference phi. Phi, it is anywhere between, here who leads? In RLC, neither current leads, coil leads. It all depends on frequency, F greater than F naught, that, XL will be greater than XC, and therefore, whenever XL is greater, current leads. For F less than F naught, that XC will be greater than XL because frequency is XC is inversely proportional to frequency, and current here it lags. Okay, L means lags. Here I leads because capacitor is dominating. But at F is equal to F naught, you all know that R leads, R dominates, and therefore current will be in phase with V. But in RL, since L is there, current should lag. And since C is there here, current should lead. Here also, R means current in phase with V. Here current lags, and here current leads. So all these ideas we get by seeing the component itself. It's a reactive component which makes helps you to make a decision. If at all, if AC is applied to this kind of a circuit, then if somebody asks you, tell me whether the current through this series combination lacks the applied voltage or leads, with the one voice you should say current lacks, because only coil is there. If capacitor is there, current leads. If both are there, then you cannot answer it unless you know the who is dominating, whether XL is greater than XC or XC is greater than XL or XC is equal to XL. And who decides all this? F. So it's F which decides, frequency which decides. With that, I'm open for questions. Back to the studio there. Thank you for the opportunity given. I think I took a little extra time. Yes, sir. Anthony, sir.
Yes, sir, I'm here.
Yeah.
Yes, sir. Yes, sir, I'm here. Sir, just 1 second. Ramesh sir will be coming.
Yeah.
Yeah, Ramesh sir will be coming.
Oh, okay. Fine. I'm there.
Yeah.
Anthony, sir, can I leave the session?
No, sir, wait, sir. Ramesh
Oh,
sir,
sure.
he said he's coming. That's why I'm waiting. Just wait, sir. Hello. Yeah. Hello, sir. Are you there?
Yes, sir. Hello, sir.
I'm sorry. The thing is,
Not a problem.
Ramesh sir is a little bit busy with the other meeting, so he has caught
That's
up
okay.
meeting. So on behalf of KSTA, our chairman, Professor Dr. S. Ayappan, and CEO Ramesh sir, and for all the colleagues, and with regards to Ambekar Eknath sir, I would like to express my thank on giving a detailed explanation on alternating current for the student. I think this will be the very detailed one for the PU students. And for me itself, it is like going over my head in between.
That's not a problem. You were
Eknath sir? Eknath sir?
Yeah, no, you were a journalism student, right?
Yeah. Eknath sir, ಏನ ಕ್ವಶನ್ ಇದ್ರೆ ಕೇಳ್ಬೋದಾ ಸರ್?
Yeah.
Yeah. Please, sir.
Hello.
Hello,
Yes,
sir.
Oh, you took me about 50 years in the time machine to my classroom in 71.
Okay.
But the clarity of your presentation, Dr. Mascaranis,
Yeah.
was very, very, very good.
Thank you, sir. I had to rush because of the
Yeah.
time, 1 hour.
But
lot of
still, it
points to
was
say. So many things are left out, but I
because
think
you
it's
were,
okay.
yeah, because you're repeating. I mean, giving the summary of each
Yes.
of your presentation every
Yeah.
time, and again
Perfect.
repeating backwards. was
Perfect.
something which was must make people to. It should be already etched in their brains
Yeah,
about
yeah.
the formulas and other things. I think
Yeah,
the formula, the mathematical relationships which you have deduced there, really must have. I mean, if you know the intuitively how the formula comes, then you will understand the thing.
Yeah, surely. Yes. Yes.
Thank you very much, Dr. Mascarenhas. And
It's
on
my
behalf of
pleasure
the-
anytime,
Yeah.
anytime to serve, yeah, the student community. Yes, sir.
So, sir, as of now, there are no questions. I just checked the chat box, and in the YouTube also there are no questions. If there are any questions, I'll send it to your email, sir.
Yeah, you can always, and I will answer them. Yes.
Yeah, sure. Yeah.
And I'll
So-
also share the notes of today's class with you.
Yeah, please, sir.
If you can send me the email ID. Okay.
Sir, the same email ID that I sent you the link in the morning.
Oh, okay. To the same, I shall follow. I mean, by
yeah.
today night, I will send the
Sure,
the
sir.
notes.
Sure, sir. That
Thank
will
you.
be helpful for the students.
Yeah, I will do that.
Yeah, thank you, sir. And coming to the last part, ಕೊನೆಗೆ ವಂದನಾರ್ಪಣೆಯನ್ನು ಕೊಡ್ಲಿಕ್ಕೆ ಬಯಸ್ತಾ ಇದ್ದೀನಿ. ನಮ್ಮ KSTA ವತಿಯಿಂದ KSTA ಮೆಂಬರ್ಸ್ ವತಿಯಿಂದ ನವೀನ್ ಸರ್ಗೆ ಅವರು ಡೀಟೇಲ್ಡ್ ಆಗಿ ಲೆಕ್ಚರ್ ಕೊಟ್ಟರು. 1.5 ಗಂಟೆ ಕಾಲದ ದೀರ್ಘ ಸೆಷನ್, ಹತ್ರ 1.5 ಗಂಟೆ ಆಯ್ತು ಇವಾಗ. ಸೊ I thank you very much, sir, for giving me a wonderful talk on this.
Thank
I
you,
thank
Mr. Anthony.
Eknath sir for joining us and bearing the time with us all the time. Thank you, Eknath sir. Thank you very much. And I thank all the students, participants who are in the Cisco WebEx and also in the YouTube. Today, to be frank, there are more people in YouTube compared to every day. Every day we used to get 10 or 12. Today it has gone till 20, 22. I do not know.
Okay.
So there are
Hopefully it will reach many more. Let's see.
So they will be watching
Hopefully
later
it will reach
also.
many more.
Yeah.
Yeah.
So thank everyone. I thank everyone at a shot. And thank you, sir. And
Thank you, Anthony. Thank you so much
link
for your
will be there in
initiative.
the
Yeah.
YouTube. Link will be there in the YouTube, Instagram, Facebook, and LinkedIn.
We shall see again.
Please
Yes.
go through it and watch it. Thank you, sir. Eknath, sir.
Thank you.
Thank you very much, sir.
Bye-bye. Bye-bye.